Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it. Planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, Director of Planetary Science at NASA, and this is Gravity Assist.
The new Solar System Podcast.
I'm here with Dr. Nicky Fox from the Johns Hopkins University Applied Physics Lab, and she is the project scientist for a fabulous mission called the Parker Solar Probe. And that's the mission that will touch the sun. And that's what we're going to talk about today. It's all about the sun. Nicky, what do we know about the sun? How does the sun really work? I mean, it's so important for life here on Earth.
Yes, indeed. So the sun, of course, is the center of our solar system. It provides light and heat to us here on Earth. We're in that perfect location in the solar system orbit where the sun allows us to live and breathe and have a wonderful life. But of course, the sun is just a very average, very basic star. Even though it's the most important thing to us, it is just an average star when you compare it with all of the others. And so it works just like any other star. In the center, there is a core, which is kind of a boiling, roiling mass of gas, very much like a nuclear furnace, and nuclear reactions go on in the center there. Hydrogen combines to make helium, etc., just like you would have in a nuclear reactor. And as that heat moves out towards the surface of the sun, it gradually cools. So the core of the sun is about 27 million degrees Fahrenheit. By the time we get to the visible surface, it's cooled to about 10,000 degrees Fahrenheit. From there, the atmosphere of the sun lifts off and moves away from the sun and bathes all of the planets. So we here on Earth, we actually live in the atmosphere of the sun.
Yeah, the analogy I use for that is it's like the sun is exhaling in all directions.
It absolutely is. And as it exhales, sometimes it sneezes. And when the sun sneezes, the Earth catches a cold.
So let's talk about some of those sneezes. We call them space weather events, but the sun can be really violent at times.
The sun indeed can be very violent, and one of the ways we use to measure the activity on the sun is you can actually count sunspots. So not that you should ever look at the sun with your naked eye, but hey, you pull up a web browser and you look at the SDO spectacular images, you see those dark spots. If you're looking invisible, if you look at them in ultraviolet, they suddenly become very bright, very active spots. The more spots there are, the more active the sun is, and that's how we characterize the solar cycle. Fewest number of spots, solar minimum. Most number of spots, solar maximum. It takes about 11 years for a full solar cycle. And during that 11 years, we see all kinds of different stuff coming from our sun. As you mentioned, there are these very intense events that we call coronal mass ejections. Literally a mass of coronal material ejected fast from the sun. We see the flare. It's followed by the very high energy particles. They travel at about half the speed of light. They can cause issues for astronauts, which is why, at the space station, we make sure that the crew area is very well protected. So NASA watches for any big events before they allow any spacewalks. They can also smash into solar panels and cause damage to spacecraft. But behind that comes the main event, the big blob of plasma. When that enters into our Earth's atmosphere, it does power the beautiful aurora, and that's a gorgeous, gorgeous effect. However, the aurora is basically a big current in the sky, and currents always need somewhere to close, and if the ground is not conducting, they will look through for long structures that they can flow through, like a power grid, like undersea pipelines, like any kind of long, straight conducting surface, and they will go through those and cause problems. They can cause catastrophic power outages, like we saw in 1989 when the Hydro-Quebec system went down, leaving 6 million people without power. It also pumps up our radiation belts, where the Van Allen probes are working and taking data for us of these events all the time, causing issues for spacecraft, either damaging with the particles. It can also cause the atmosphere to become much more dense, slowing down a spacecraft and changing its orbit, which has to be, mitigated. Many effects of space weather causes problems for GPS. It can cause outages or even just, problems with how accurate it is. And we all rely on our GPS to get us everywhere, every day. So we really do rely on technology, and technology is very much affected by the sun.
Well, that's a fascinating topic, space weather. We just need to know much more about it and have the ability to predict it. So as humans take off and leave low Earth orbit and go beyond, the moon and out into the solar system, perhaps to Mars next, understanding space weather will be really critical. Now, Mars doesn't have a magnetic field, and the solar wind, which hits us, and we are pseudo-protected, I'd say, because of our magnetic field. Mars and many of the other objects, even Venus, really can get hit by the solar wind. So what happens when those things occur?
Well, so then you're really looking at the radiation effects because, as you say, you don't have the magnetic field to protect you. Also, with such a very weak atmosphere, there's really no way for it to absorb the heat from the sun and keep it. And so you're really looking at direct radiation effects. And so, yes, we can certainly travel to these other planets. We just want to make sure we understand both the cosmic rays that are coming from outside our solar system and also the solar wind particles and the very energetic stuff coming from the sun. We need to understand both of those and make sure that we correctly shelter our explorers.
As a magnetospheric physicist, I love anything with a magnetic field, and even those things that lost their magnetic fields in the past. And so it's been clear from the research that's been going on for the last several decades that when there's that coronal mass ejection that hits the Earth, we always get aurora. And so indeed, those events are intimately linked.
They certainly are. So when this material, or as you put it, when the sun is exhaling and it puts all that material out, as the material is accelerated, it grabs the solar magnetic field with it and it carries it out towards the Earth. Just as you remember from high school, like poles repel, opposite poles attract. So if that field in this solar wind is pointing in the opposite direction to the Earth's magnetic field, they will attract, they will connect, and they will let all of that solar plasma come into our atmosphere. There's a process that occurs, we call it magnetic reconnection, but it's basically all of this excess magnetic field getting moved back around to the sun side. When that happens, all of these energetic particles come streaming down the magnetic fields and they impact our Earth's atmosphere. Our Earth's atmosphere is predominantly nitrogen and oxygen. When it gets struck by these really high energy particles, it actually excites the molecules and atoms in our own atmosphere and causes them to glow. And that glow is what we see as the aurora. It's kind of like giving a 2-year-old sugar. You dump a whole bunch of energy in, it gets totally excited, and then it goes right back to how it was before you gave it the sugar. It's just like that with the aurora. You dump a whole bunch of energy in, it lets off a tremendous amount of light, and then it goes right back to the atmosphere that we had before the event.
Well, that sugar event, as you said, really starts in the tail of the Earth when there's a reconnection that occurs that accelerates the particles that create the aurora. But reconnection as a physical phenomena, it doesn't happen just at the Earth. The coronal mass ejections, there's also reconnection that occurs with that. But there's another phenomena on the sun, not like a coronal mass ejection, but equally important, and that is solar flares.
Absolutely, yes. And they often occur right before a coronal mass ejection leaves the sun. Those magnetic field lines that you see, the sun has a magnetic field very similar to the Earth. It's a lot more complex, but it's still got a magnetic field. These little loops can pop out. And if you look at really nice SDO images, you can often see these long loops of sort of illumination. And as they get stretched and stretched, like an elastic band here, if you stretch it and stretch it, at some point it will break. When it breaks, you always feel pain in your hand because you snapped an elastic band. That pain is actually the heat coming from the band into your fingers. So as you stretch these magnetic field lines at the sun, they become more and more and more energetic. You're putting more into it. At some point, they will burst. When they burst, they let off a whole bunch of energy in all kinds of different forms, and one of them is visible light, and that's when we see a flare.
The really study of the sun that we do has all been very remote. And some of the things that we've been talking about, have been observed and then assumed that these kind of things occur, and how particles get accelerated through a magnetic reconnection. But in reality, we've really got to go there and we've really got to make some measurements right where some of this action happens. And you're involved in a fabulous mission called the Parker Solar Probe. Can you tell us a little bit about it?
Yes, well, Parker Solar Probe is the coolest, hottest mission under the sun. And for the very first time, we are going to go into this region. We're going to go and visit this area where kind of all the magic happens. So we've done so much with remote sensing. We really have. We've done a lot with measuring even the solar wind out around Mercury. But everything happens in that coronal region, in that hazy atmosphere around the sun. And in that atmosphere, first of all, we have two mysteries. One is that material itself is actually hotter than the visible surface of the sun, about 300 times hotter, with, temperatures around 3 million degrees. And yet the surface is about 10,000 degrees Fahrenheit. So, there's a big mystery. If you walk away from a campfire, you get colder, not hotter. But if you walk away from the sun, you would suddenly get into a much hotter region. Where this big temperature happens, the plasma itself gets so energized that it can actually break away from that huge gravitational hold of the sun and form the solar wind, bathe all of the planets. So these are these two mysteries we have. Why is the solar wind born there? Why is it so hot? And why is it so accelerated so much? And we've done an awful lot. We've postulated theories. We've actually learned an awful lot about our star. But that's the kind of final piece of the puzzle. Going up and visiting is the key here. If you look out of the window and you see it's sunny, great, it's sunny, but you have no idea how hot it actually is. You don't know if the wind's blowing. You really need to go into that atmosphere and experience it. And so for the very first time, Parker Solar Probe will journey into the sun's corona and take those key missing in situ measurements.
Now, when it gets launched, it's going to fly not directly to the sun, but it's going to make some encounters with some of the planets. What's the plan?
Yeah, so our launch window opens July 31st, 2018, and we launch out of Cape Canaveral. And our first encounter is with the planet Venus. So we launch and we're moving so fast when we launch. We're on a Delta IV Heavy, which is the biggest rocket currently in NASA's arsenal. And we also have an upper stage on top of that to really make us blistering speeds as we're leaving the Earth. So it just takes us 6 weeks to get to the planet Venus. And we do our first gravity assist around Venus. Now, Jim, I know that you're very used to missions using gravity assists to speed up. New Horizons went to Jupiter, shot around there and came out much faster. So we're actually very generous. We're giving energy to Venus. We're not using Venus to speed up. We're actually using Venus to trim our orbit very slightly and very carefully to allow us to move around the sun in very big petal orbits. And we actually encounter Venus 7 times during our 7-year mission. And each time we just trim our orbit just a little bit to allow us to gradually walk closer and closer to the sun with our closest approaches until in our final configuration, we are just under 4 million miles away from the sun's surface. And I realize when I say 4 million miles, you think, well, that doesn't sound particularly close. But if you put the Earth and the sun 1 meter apart, Parker Solar Probe will be at 4 centimeters from the solar surface, and that is close.
We just ended Cassini by having it plow into the atmosphere of Saturn, and that ended it. Is the plan that Parker Solar Probe will end by plowing into the sun?
No, I hate that question. I really do. It's such a sad end for us. So we go 7 years, as I mentioned, as our prime mission. After that, the final orbit is totally stable, so we can stay in that orbit and continue taking science as long as we still have fuel on the spacecraft. So we basically use momentum wheels to keep our spacecraft oriented so our wonderful heat shield remains between us and the sun at all times. However, these wheels do need to be despun. Every now and again, we do need to fire thrusters. And so at some point, we will run out of fuel and we won't be able to keep that heat shield where it needs to be. At that point, the spacecraft will start to turn. that means that the sun is now hitting parts of the spacecraft that are not designed to have the sun on it. So the spacecraft at that point will start to break up and, eventually will join the dust cloud around the sun. And it'll be a very sad day.
Yes, it is. So many people work on our missions and really devote a significant part of their career to make them happen. The return, of course, is the data and the observations that they make will live on forever and will be archived and studied, and we'll learn an enormous amount. And that's why we build these spacecraft, to do these things.
That's true. And of course, with Parker's solar probe, people have devoted decades and decades of work to this because Parker was first proposed in 1958, around the time that Gene Parker put out his seminal paper really postulating what was happening around the sun and in fact named the solar wind. And so, since 1958, it's been the highest priority mission in many decadal surveys and many NASA roadmaps. And it's taken us nearly 60 years to finally have the technology available to us to do this, to really make our dreams come true. So, talk about pioneering spirit. People have donated 6 decades of their life to making this happen. So we're all very proud of this mission.
Yeah, I think it's aptly named. Eugene Parker was really a fantastic scientist and took a lot of heat, no pun intended, when he actually proposed that, the sun should be outgassing. It should be losing matter through a process called the solar wind. And wasn't really originally believed. It really took our first successful planetary mission, Mariner 4, which went by Venus and also measured the solar wind for the very first time to then validate that his theories and ideas were indeed correct and the start of what we now know about space weather.
Yes, that's right. And of course, the big thing was showing that it was going much faster than people would expect. If you pump the gas on a car and then you let it just slow down, it slows down fairly quickly. If you just think of dumping a bunch of energy into the coronal material and letting it accelerate, you would expect it to slow down very quickly. You would also expect it to cool down very quickly. But of course, those first measurements showed us that it was moving faster than you would predict if you just use basic adiabatic equations, and it's way hotter than we would expect, even out around Earth.
I'm here with Nicky Fox, and we're talking about the sun. One of the things that happened most recently was the eclipse. It now looks like that maybe 85 or more % of the entire U.S. population had an opportunity to see it. Now, with the Parker Solar Probe going into the corona and really tasting it, that solar eclipse gave us an opportunity to see the corona for our own eyes. Where were you when that happened?
So this was actually my first solar eclipse, and I was in Beatrice National Park in Nebraska with about 10,000 people supporting a NASA event.
A beautiful area, I might add.
It is a beautiful area. And it was the only problem for me was I dragged my entire friends and family with me, and then it was cloudy. And in fact, after the beginning of the eclipse, it even started to rain. And we were very, very lucky that right at about totality, the clouds parted and we actually saw the most amazing corona, the most fantastic diamond ring. It was a truly spectacular, truly momentous occasion. And not only that, I actually could see the part of the sky where Solar Probe will be living and working. So it was very exciting.
Yeah, I know. I know that connection. I received it too. I was in Idaho Falls at the Idaho Falls Museum. And this was my first eclipse, and as it was really kicking off and it was getting very dark, all I could say is, oh, wow. And then I saw Venus. I guess as a planetary scientist, I couldn't not comment on where Venus was, but...
You should have seen all 4 planets.
Well, Venus popped up right away. Then, unfortunately, the streetlights came on in
no.
the town. The sun, in addition to the solar wind, gives off a significant amount of light. And that light, as it moves away from the sun, is reduced in intensity because of the distance and the directions it travels. Here at Earth, we're just, I think, at the right place. We call it the Goldilocks zone.
Yes, that's right. We see one sun here at Earth. solar probe, by the way, will see 478 suns at its closest approach. But absolutely, we are at the perfect location. We have the right atmosphere that allows the sun to warm our planet and make it habitable for all of us. It wouldn't be so pleasant trying to live out on Neptune, I don't think.
Right, hardly any solar wind gets there, but it decreases in intensity as it also goes out away from the sun. It's being measured by New Horizons and many of our other spacecraft, even the Voyagers. You know, as the sun's magnetic field is moving out with the solar wind, that's got to stop at some point. What do we know about that?
And so we do know that our solar system has a finite boundary. We call it the interstellar boundary. And it's where we move from the space that our sun is dominant over into the space where the sun no longer has any real influence. And, the Voyager spacecraft crossed that boundary and is now out in interstellar space. And we continue to learn more and more about the boundary with our great observations, in particular the IBEX spacecraft that has actually managed to image this heliopause, this sort of final boundary from our solar system out into interstellar space, and found a ribbon structure along there, and has actually promoted a new mission to be proposed in the Decadal Survey called IMAP, which is going to take it kind of to the next stage. With IBEX, we've found all the questions we want to answer, and now with IMAP, we'll take it one step further and actually bring answers to those questions.
It was also thought at one time that the heliopause, like the Earth's magnetosphere, had a very blunt front end in the direction that the star is moving around the center of our galaxy, and then a long tail. But some recent observations, particularly those from Cassini, instrument on Cassini, has indicated that it's a little different than that. What have we found out?
So we found that it almost breathes. The boundary is not a fixed place. It's sort of moving in and out. And we think it's actually, to do with our solar cycle, as the sun's influence kind of changes with the solar cycle. And so this boundary is not a fixed boundary as we first thought it was, but it's changing in time, just like everything else in our solar system. As the sun changes, everything feels an effect, even the boundary with interstellar space.
With Parker Solar Probe getting gravity assist from Venus and allowing it to meet its objective, I always ask my guests, what was your gravity assist that really propelled you into this field and kept you going?
My gravity assist happened at a very early age, and it was my dad, because he was fascinated by everything NASA, everything space. Instead of bedtime stories, I would get how the sun was in the center and the earth went around the sun and the moon went around the earth. And I remember, glasses being used to show me how the orbits worked. And he was totally followed every single thing that NASA did and absolutely loved it, and instilled in me the idea that the best possible thing I could do would be to work for NASA. And I think that even, as a girl in England where you don't think that really is possible, there was still this sort of magical thought that stayed with me that, okay, I'll probably end up doing something different, but gee, it would be great to work for NASA. And so, I went through college and I did space plasma physics. And then a very good friend of mine, Dr. Jim Slavin, came up to me and said, could I interest you in a job at NASA? And that was probably my final gravity assist.
Yeah, Jim will do that. He's a good friend of mine, too. Well, thanks so much, Nicky. It's just been a delight talking to you. So until next week, I'm Jim Green. This is Gravity Assist.